Dave Stallman here. We're continuing our discussion of geometric series, and we have another series to look at. 100 plus 10 plus 1 plus 0.1 plus ... So this is an interesting series. One, because it's infinite, it goes on forever, and two, it's shrinking instead of, or the sequence is shrinking. It's going 100, 10, 1. The numbers are getting smaller and smaller and smaller. So let's see if we can figure out how to write an explicit equation to describe this sequence of numbers which added together make a series. So the first thing we need to do is determine whether it's arithmetic or geometric. And it looks like we are dividing by 10. But for geometric series, we always think in terms of what do we have to multiply by. And the way that we can get this is we can take the second term divided by the first term, and that will give us the common ratio. So regardless of the geometric sequence, you can always get the common ratio by doing the second term divided by the first. So we know now that our common ratio is 0.1, and if you do 100 times 0.1, you get 10. 10 times 0.1 is 1. 1 times 0.1 is 0.1, and so forth. In fact, our next term would be 0.01, and then our next term would be 0.001, and so forth. The other thing that we need is the value of the first term, which is 100. So if we want to write an explicit equation to describe this sequence of numbers, the nth term is equal to the first term times the common ratio to the n minus 1 power. Question 2 says, write the series using summation notation. Okay, so we're going to start with our sigma, which stands for sum up all the numbers in the series, and then we're going to write our explicit equation, and then we are going to identify which term we're starting with, which is the first term. And since this is an infinite series, it goes on forever. Okay? So the last part is to evaluate the series. And this is rather interesting because these numbers keep getting smaller, and so I'm curious what's going to happen. Well, we start with 100, and then we add a 10, and so we get 110. And then we add a 1, so we get 111. And then we add, let's see, I should put the plus signs in here, a 0.1, so we get 111.1. And then our next term is going to be 0.01, and so we get 111.11, and so on and so forth. Well, this is kind of crazy. 111.111, on and on and on. Well, what is this eventually going to add up to as we go off to infinity? I don't know. It's interesting. Let's take a look at a graph and see if this can help us. And let's go the n value on the x-axis, and then let's put the sum on this axis. And so with 0 terms, we don't have any sum at all. But when we're at n equals 1, when we add up the first term, we have 100. And then we add the second term into it, and so we get 110. And then we get, after the third term, we get 111. And then the fourth term, we get 111.1, and then 111.11, and 111.111. And it looks like we have a sequence that's summing to something like this. And I might ask you, do you think that this is ever going to reach 112? Well, it looks like we're just going to continue adding these ones here, and it's never really going to reach 112. And so this series exhibits asymptotic behavior, which means that there's an asymptote up here somewhere that no matter how many terms that we sum together, this is never going to exceed a certain number. And in fact, you know, if we just keep adding ones here, it looks like that this asymptote is not really 112, but 111.1 repeating. So, in a sense, we're saying that this summation converges or approaches 111.1. So this is what we would write. We would write the sum of n equals 1 to infinity of 100 times 0.1 to the n minus 1 is equal to 111.1 repeating. The sum converges on 111.1 repeating. Now, in our previous example, we had a sum that did the opposite. It grew exponentially and it diverged. It exploded. It just got bigger and bigger and bigger. And the question would be, what's the difference between that one and this series? And the difference is that the R value for this series is less than 1. And that's what makes this converge. And so there's a rule here, and it goes like this. Convergence or divergence is determined by the common ratio. And here's how it goes. If the absolute value of the common ratio is less than 1, the series converges. And so we have a situation of convergence. If the R value, the absolute value of the R value, the common ratio, is greater than or equal to 1, the series diverges, or we have a condition of divergence. Okay? Now, as it turns out, if there's divergence, if the R value is greater than 1, there is no sum. It diverges, it explodes. However, if the R value is less than 1, then what we can do is we can say that for an infinite geometric series, if the absolute value of the common ratio is less than 1, then the series converges on the following sum, which is given by A1 divided by 1 minus R. where A1 is the first term to be added in the series, and the R value is the common ratio. Now, let's check that for this problem that we just did. So, if this equation holds true, we should be able to put this formula in and get 111.1 repeating. And so our starting term is 100, and we are going to divide by the parentheses 1 minus our common ratio, which was 0.1, and there it is, 111.1 repeating.